So in this final vodcast for standard level, high level core cosmology, we'll look at the accelerating universe, which is a fairly recent development of our understanding of the universe. We'll also look at how to describe the scale of the universe and how it changes and how that relates to redshifts, particularly extreme redshifts. We're using a couple of the equations that you can see there from the data booklet. We've seen this slide before. This is the basic Hubble relationship, which says that the distance of a galaxy and its redshift are directly proportional, with a constant of proportionality being given by Hubble's constant. And we have a value for Hubble's constant that we have previously discussed. But since Hubble's time, by the development of advanced telescopes and things like the Hubble Space Telescope, we're able to take much more detailed looks at distant objects in the universe. Here is an example. This is the Hubble Extreme Ultra Deep Field, where scientists, astronomers pointed the Hubble telescope at a very, very small patch of sky for a very long time to record the faintest objects that they could. And in this entire picture, you can only see, I think, 2 or 3 stars. I think if you can see the cursor, there's one star, there's another. Every other object in this image is a galaxy, some relatively close by and well defined, some much fainter and much more presumably distant. And by analysing the motion of these most distant objects and some of the stars within them, we are able to make some interesting observations about the universe. Now, to describe the redshift, well, let's start off with just looking at the standard equation for redshift. The standard equation for the electromagnetic redshift, because acoustic redshifts are somewhat different, is that the fractional change in the wavelength or the frequency is given by the fractional change of the speed of the object compared to the speed of light. So if the fractional change was 10% difference in the frequency or 10% difference in the wavelength, then you would be traveling at about 10% of the speed of light. By the way, I often wonder when you see these about symbols, well, okay, what's the actual formula? Well, that will give you a more precise version, but to be honest with you, that V over C is perfectly adequate for us. Now, this ratio is obviously an important quantity, and so therefore we give it a code which I will call Z. I'm aware other people might pronounce that letter differently, but I will be pronouncing it Z. So Z is proportional to the fractional change in the frequency, which is the same as the fractional. It's defined, not proportional, so it's defined by the fractional change in the frequency, or equally the fractional change in the wavelength, and it's approximately equal to V divided by C. The other thing that we need to define is the scale factor, which is actually the R here. To give you an idea of what the scale factor is, it's very similar. It's a fractional change. It's a fractional change in the distances within the universe, or in this case, within the bread. So this is our raisin bread, which is being baked, and the dough is rising, and the raisins are all moving apart from each other. So in this case, we would say that fractional difference, the value of Z, if you like, is the amount it's changed by. So from A to C has gone up by 5, so it's delta R equals 5, divided by the original length of 5. And that the same applies, increase by 16 divided by 16, increase by 1 divided by 1. So in this bread, in this universe, the value of Z here is 1. So the two important relationships are, first of all, this fractional change in the wavelength is proportional to V over C, and also this value of Z is equal to the fractional change in wavelength, but is also equal to this change in the scale factor. This change in the scale factor is also able to be written because delta R, change in R, is the final R minus the initial R, divided by the initial R, which we can modify to say R over R0 minus 1. So Z equals R over R0 minus 1, and Z equals delta lambda over lambda, or delta F over F equals V over C. So a couple of definitions there. Let's actually apply that information. This is not quite the Hubble Ultra Deep Field, but it's a similar sort of thing. It's a very detailed, very long exposure photograph of a patch of sky in the direction of the constellation of Orion. And again, the vast majority of these extended or even point sources of light that you can see are distant galaxies. And there's one which is at the middle of these crosshairs, which you can barely make out here. Now, I'm recording this in early March of 2016, and this observation was actually done, or the paper was published, on the 3rd of March 2016. So as of right now, as of me recording this, this object is the most distant object beyond the background, apart from the background radiation itself, that we have detected. The most distant single object, a galaxy. This is actually a complete galaxy. And it has a measured Z value of 11.1. Now that's, by the way, it's a ratio, so Z does not have units. So using our information, Z equals V over C, which means that the velocity of that object is 11.1 c. Now that takes a moment. Let's take a moment to digest that. That's not, so to speak, the velocity of the object in this photograph, as seen in this photograph, because we're detecting the light from that object as it was emitted 13.4 billion years ago. That object today, because it will still exist in some form, probably, that object today is traveling away from us at 11.1 c. That means that any photons that are emitted from that object today will not be visible in 13.4 billion years or in any time in the future. That object is probably of the order of 70 to 90 billion light years away and is far outside of our observable universe. Our observable universe is just one portion of the universe entire, which many people believe to be infinite in extent. The observable universe is defined by the objects which at this moment in time are emitting photons which will eventually at some future date reach the Earth. Okay, it's quite a complicated process if you look at it in detail. There are links on the website. Go search for YouTube channels. It's a fascinating topic. Okay, but from the information, we can tell you that that object today is moving away from us at over 11 times the speed of light. It's not, again, it's not moving through local space at 11 times the speed of light. Okay, it's impossible to move through local space faster than the speed of light. But when we're saying the velocity of that object, that velocity is due to the expansion of space itself. So space is getting bigger. And the further away something is, the bigger that is. Again, it's like our raisin dough here. Okay? If we had a big enough bread, then raisins would be expanding greater than the speed of light. But the raisins themselves are not actually moving relative to the dough in which they are embedded. It's the dough itself that's expanding. Hope that makes sense. The other piece of information is to scale factor information, which can tell us the size of the universe as a percentage of ours when this was emitted. So r over r0 minus 1 equals 11.1. Therefore, r over r0 equals 12.1. Therefore, r0 over r equals 1 over 12.1 equals 0.083. So r0 as a fraction of r, the length when this was emitted as a fraction of our current length, is about 8%. So the universe was only 8% of its current size. And as I said, this GN Z11 is currently the most distant observed object that we know of in the universe. Slightly closer to home, a galaxy like this, we can see supernovae. Now, supernovae come in different types, and if you're in the high-level course, we'll look at this in a bit more detail. All you need to know is that there is a type of supernova at the moment called a type 1a. And that type of supernova has a very clearly defined light curve, and that light curve leads us to an equation which enables us to determine the absolute magnitude, in other words, the luminosity of the object. And once we know its luminosity, it becomes a standard candle. Because we know its luminosity, we know its measured brightness here on Earth, and therefore we can use the traditional B equals L over 4 pi r squared formula to find the distance between us and it. And people did this. And what they found was that the brightness of these supernovae was not what they expected it to be. And the only explanation of that was that the universe is expanding, and that expansion is accelerating. And this is very unusual, because people had previously assumed, for good reasons, that gravity would be slowing the expansion of the universe. The universe is expanding, but since it is filled with objects and those objects exert gravity on each other, that expansion would be slowing. Whether it was enough to stop the universe entirely and maybe reverse its expansion so it would contract into a big crunch or something, unknown. The evidence seemed to be suggesting that as near as damn it was probably going for the critical density of expanding forever, but eventually at some point in infinite time coming to a stop. But the data does not support that hypothesis. This is a classic example of a completely, totally unexpected result, which in the last 10 years has completely changed our perception of the universe, because the data did not support that hypothesis. It was a great hypothesis. Early evidence seemed to support it. Theories seemed to support it, but the final and most recent data does not. And this was the cause of the award of the 2011 Nobel Prize in Physics. So this supernova data is in fact telling us that our universe is expanding, and unless we learn something new in the future, it will continue to expand faster and faster and faster and faster, which has the perverse effect of actually making our observable universe ever smaller, because it's carrying the objects further and further away from us at an accelerating rate. This nice chart from the WMAP people describes our current picture of cosmology. First of all, there was a beginning, random quantum fluctuations or something like that. Then there was very rapid inflation, followed after 380,000 years by the universe finally becoming transparent. Anisotropies can be observed in this afterglow. Then there was the Dark Ages, because this time was when the neutral hydrogen could be created, and helium, and the first stars were formed about 400 million years, which is about the age of that galaxy we just saw. That galaxy was very much formed from those population-free primeval stars. The universe is expanding. The expansion rate is very slowly slowing, but sometime about 5 billion years ago, the slowing of the expansion stops and then reinvigorates, and it is accelerating at an ever greater rate. The velocity of the expansion is increasing at a greater rate. So it comes to today just over 13.7 billion years later. Just to finish with some predictions, a man called Freeman Dyson wrote a very famous paper on what might happen in the future universe. It's pretty conjectural. But what will happen to us, what will happen to the Earth? Well, in about 2 billion years, the gradually warming sun, if you remember, the sun over its main sequence lifetime slowly moves in the main sequence, slowly becoming more luminous. That will lead to a runaway greenhouse effect, which will render the Earth uninhabitable. In about 5 billion years, we'll have the final red giant stage phase, and the Earth is destroyed or reduced to a cinder. Go ahead a good 20 more times or so to 150 billion years, and the expansion of the universe will take all but our local group out of view. On a local scale, our local group of galaxies gravitationally bound to each other, that effect is bigger than the expansion. That date, by the way, is probably a little bit optimistic because of the more recently discovered accelerating effects. Moving forward to 100 trillion years into the future, probably all of the interstellar gas and dust will be used up, there will be no more new stars, and we will come to the end of what is known as the stelliferous age. But the universe is still just a baby. It will take 10 to the 30 years for all of the stars, all of those low mass red dwarfs to die, turn, fade into black dwarfs, all that material to slowly be nudged and gather, probably into supermassive black holes. And then it will take up to 10 to the 98 years, another 70 or so orders of magnitude, another 70 times the entire life of the universe, up to that unimaginably distant point, for those supermassive black holes to evaporate by Hawking radiation, and the last of what we might call matter in this universe will be converted to pure energy, at which point, game over. Because if you've got pure energy, you have no change, you have no energy gradient, you have no matter to do any change, no structure. And without any of those things, then the concept of time is pretty much meaningless, and the universe will cease. And that's the end of the podcast. Thank you very much.